Hi guys, we're on the last lesson of this module, page 123. It is lesson 13, comparison of numbers written in scientific notation and interpreting scientific notation using technology. We're actually only doing the first portion and only some of them due to the fact that we're not in class around our calculators and whatnot, so we'll come back to that when we return to the classroom. So, first off, in the box, there's a general principle that underlies the comparison of two numbers in scientific notation. Reduce everything to whole numbers if possible. To this end, we recall two basic facts. Inequality A, so let x and y be numbers and let z be greater than 0, then x is less than y if and only if x times z is less than yz. Also, the comparison of whole numbers. If two whole numbers have different numbers of digits, then the one with the more digits is greater. Also, suppose two whole numbers p and q have the same number of digits, and moreover, they agree digit by digit, starting from the left until the nth place. If the digit of the p in the n plus 1th place is greater than corresponding digit in q, then p is greater than q. So we're going to look at those type of ideas if they are a little bit complicated in exercise 1, 2, and a couple more on the back. All right, so I know that I had started doing this just because it's so much numbers that I didn't want you guys to mess up, so I'm going to explain things. The Fornax dwarf galaxy is 4.6 times 10 to the 5th light years away from Earth, while Andromeda is 2.430 times 10 to the 6th light years away from Earth, which is closer. So you're comparing these two numbers, which have a different number in front, and then the exponent is different there. So what you want to do is you want to change Andromeda 1, this is Andromeda 1 right here, from what is said, right, if we write it 2.430 times 10 to the 6th, which is equal to 2.430 times 10 to the 5th, because that's 10 to the 6th right there. And so that's equal to 24.30 times 10 to the 5th. So now you're comparing this number and this number, which is a lot easier to do because you have your exponent the same, and so you really are just comparing that first number there. So because 4.6 is less than 24.30, then 4.6 times 10 to the 5th is less than 24.30 times 10 to the 5th. And since 24.30 times 10 to the 5th is equal to 2.430 times 10 to the 6th, we know that 4.6 times 10 to the 5th, which is Fornax dwarf, is less than 2.430 times 10 to the 6th, which is Andromeda 1. Therefore, Fornax dwarf is closer to Earth, is really the point there. And that's the reasoning. We're going to look at doing that a different way in this next one. Exercise 2, the average lifetime of the tau lepton is 2.906 times 10 to the negative 13 seconds, and the average lifetime of the neutral pion is 8.4 times 10 to the negative 17 seconds. Explain which subatomic particle has a longer average lifetime. So look at the tau lepton, it's right there. And what I did, just because this is maybe another way that you'd want to do a problem like this, is I'm just expanding it out to standard notation. So I could see, like if you do get confused, always expand it out and it makes things easier. It's kind of like going backwards. So 2.906, and then I'm going negative 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 is times I'm moving the decimal. Okay, I could write all those zeros right there just so I could see. It's very small. And then you have the natural pion, which is 8.4 times 10 to the negative 17, so you're going further back. So now you might be able to see, oh, this is even going to be smaller. It's going to be more zeros, which means it's smaller, because we have a decimal and more zeros. So what you would want to say there for this one, which is, sorry, I lost my place, is the tau lepton, right? Tau lepton has a longer average lifetime. Yes, it's still very small, but this is smaller. Okay, and on the back, we're gonna take out that exploratory challenge. It's not really filling in our objectives for the unit. And then we have exercise 4, which you're comparing 9.3, sorry, get a little focused, times 10 to the 28th times 9 and 9.2879 times 10 to the 28th. So what you would notice here is that is the same thing. So really you're just comparing these two numbers. And so if I just take those and multiply them times like 10 to the 4th, just to expand them out, what I see is 93,000 is greater than 92,879, right? And 9.3 is greater than 9.2879. So therefore, 9.3 times 10 to the 28th is greater than 9.2879 times 10 to the 28th. And you might be saying, well, duh. But all of these confusing things that you read here, that is what they mean. It's like, if it's bigger, it's bigger. Okay. And then exercise 5, which said that Chris said that 5.3 times 10 to the 41st and 5.301 times 10 to the 41st, or sorry, is less than 5.301 times 10 to the 41st because 5.3 has fewer digits than 5.301. Show that even though his answer is correct, his reasoning is flawed. Okay, show him an example to illustrate that his reasoning would result in an incorrect answer. So I just drew an arrow up here because this is proof, right? This is an example of one where, yeah, we have fewer digits here than here, but it's greater. So that example proves that that example is wrong, or that his reasoning is wrong, I should say. Okay, so that's actually the last part we're going to do. We're going to skip the exploratory challenge that follows this, and so you can go do the assessments, and then we'll wrapping up lesson or module 1 the next couple days. All right, bye.